The King of the Hill triathlon race in Kinsale consists of a 750-metre swim, followed by a 20-kilometre cycle, followed by a 5-kilometre run. The questions below are based on data from 224 athletes who completed this triathlon in 2010. Moira is analysing the data from the race using statistical software. She has a data file with each competitor's time for each part of the race, along with various other details of the competitors. Moira produces histograms of the times of the three events. Here are the three histograms. So here's the swimming histogram. So the x-axis represents time in minutes. The y-axis represents competitors. Remember, histogram is like a bar chart, but it's where the bars are all stuck together, and it's for continuous data. Here we see the histogram of the cycle, and here we see the histogram of the run. A. Use the histograms to complete the following sentences. Number 1. The event that, on average, takes the longest to complete is the cycle. So the cycle takes the longest to complete, and this is the reason why. Looking at where the largest number of competitors lie for a given event will tell us the estimated average. For the swim, the average is somewhere within the 14 to 20 minute range. So if we have a look at swim, we can see the highest bars start at 14 and go up as far as 20. So our x-axis is going up in twos. So we have 10, 12, 14, 16, 18. Just zoom in so we can get a better look at it. So 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. And we can see that these three bars are the highest bars, and they start at 14 and they end here, which is 20, because halfway between 18 and 22 is 20. So these three bars are the highest bars. So again, for the swim, the average is somewhere between 14 to 20 minute range. Then for the cycle, the average is somewhere in between the 36 to 46 minute range. So let's zoom in on the cycle. So here we see again our x-axis is going up in twos, and we see that these are the highest bars in our x-axis, and they range from, that would be 36 up as far as 46. And again, this is in minutes. And for the run, the average is somewhere in the 22 to 28 minutes range. So again, we'll zoom in on the run. And again, the x-axis is going up in twos. So we see the highest bars go from 20 up as far as 28. So the swim takes on average between 14 to 20 minutes to complete. The cycle takes on average between 36 to 46 minutes to complete. And the run takes on average between 22 and 28 minutes to complete. So clearly 36 to 46 minutes is the longest. So cycle is the event that on average takes the longest to complete. Number 2. In all three histograms, the times are grouped into intervals of 2 minutes. So we had already actually said in the previous slide that each of the x-axes in each of the histograms is going up in twos. So 10, 12, 14, 16, 18, 20, 22, and so on. So we can determine this by examining the x-axis of each histogram. Part 3. The time of the fastest person in the swim was between 10 and 12 minutes. So reading off the histogram, the first non-zero column lies in this interval. So let's have a look at swim. So if this is the time in minutes that the competitors completed the swim in, then the smallest amount of minutes would be the fastest time. So since between 0 and 10 there's no bar whatsoever, that means nobody completed the swim between 0 and 10 minutes. But we see there's a small bar, so this could be 1 or 2 people completed the swim between 10 and 12 minutes. So that there represents 12. If this is 14, then halfway between 10 and 14 would be 12. So 1 or 2 people completed the swim somewhere between 10 and 12 minutes. We don't know exactly how long it took them. So this would be the fastest time between 10 and 12 minutes. And likewise, the longest time would be that there looks like probably 1. So between 30 and 32 minutes would be the longest time. So the time of the fastest person in the swim was between 10 and 12 minutes. The median time for the run is in the 24 to 26 minute interval. Okay, so we have to have a look at the run histogram to come up with this. So we're going to set up a table. The first column will be the time interval, so 16 to 18, because 16 to 18 is the first bar, then 18 to 20, because 18 to 20 is the second bar, and so on, down as far as 36 to 38, because 36 to 38 is the last bar. Then we need to fill in the number of athletes. So this will be an approximation, but between 16 and 18 there was 2 athletes. So between 16 and 18 it goes up to about 2. Between 18 and 20 it goes up to about 15. So between 18 and 20 it goes up to about 15. Between 20 and 22 it goes up to about 25. Between 22 and 24 goes up to about 45, and so on. So we fill in the number of athletes. So given that there are 224 athletes, and we were told this in the question, the median is the value such that 112 athletes had a slower run time than this value, and 112 athletes had a faster run time. So 224 divided by 2 is 112. So 112 athletes had a slower run time than the median, and 112 athletes had a faster run time than the median. So we will estimate the number of entries in each time range for the run to determine where this median should lie. So we came up with the time intervals, so they're definite from the x-axis, and then the number of athletes was estimated from using the bar chart. So now what we have to do is get the cumulative values. So we start with 2, and then so we just write 2 in the very first box, and then we add on the next number of athletes, which is 15. So 2 plus 15 is 17. Then we add on the next number of athletes, which is 25. So 17 plus 25 is 42. And then we add on the next number of athletes, so 42 plus 45 is 87. And then 87 plus 65 is 152. And then 152 plus 35 is 187. 187 plus 15 is 202. 202 plus 12 is 214. 214 plus 8 is 222. 222 plus 1 is 223. And 223 plus 1 is 224. And that's what we should get to, because again we were told in the question that there's 224 athletes. So we should hopefully get to 224 or thereabouts, because remember this would have been an estimation from the graph. So note that there are 87 athletes who had a run time of 24 minutes or fewer, but there are 152 athletes who had a run time of 26 minutes or less. So where did this 87 come from? Well, we can see in the table that, so cumulative is where we're adding as we go along. So up as far as 87, this is adding all the athletes up as far as the 22 to 24 minute range. So we've added the 2, the 15, the 25 and the 45 to get to 87. So we've added them all together. So there was 87 athletes who ran less than 24 minutes. So 24 is the highest value in that range. So 87 athletes who ran less than 24 minutes. And then there was 152 athletes who ran 26 minutes or less. So 152 athletes, so all these athletes have been added together. So 2 plus 15 plus 25 plus 45 plus 65 is 152. So all of these athletes ran less than 26 minutes. So altogether there's 152 athletes who ran less than 26 minutes. And altogether there's 87 athletes who ran less than 24 minutes. So 87 athletes who ran less than 24 minutes. 152 athletes ran less than 26 minutes. And we know our median is 112. And we know 112 is somewhere in between 87 and 152. So that means that the median run time is between 24 and 26 minutes, so in between these two values. So the median is in the 24 to 26 minute interval, because we know that 112 is somewhere in between these two values. So it can't be the 22 to 24 minute range, because there was up as far as 87 athletes, so we need to add on a few more to get to 112. So it must lie in between the 24 to 26 minute range. 5. The event in which the times are most spread out is the cycle. We want to find the event which has the largest time difference between the fastest and slowest competitors. For the swim, the difference is 30 minus 10, which is 20. So 30 minus 10 is 20, so that's the range for the swim. For the cycle, it's 58, take away 30, which is 28. And for the run, 36, take away 16, which is 20 minutes. So the event in which the times are most spread is the cycle. So 28 minutes is the biggest range. So between 20, 28 and 20, 28 is the biggest range. B. Maura is interested in the relationship between the athlete's performance in the run and in the cycle. She produces the following scatter diagram. So run versus cycle. Part 1. The correlation coefficient between the times for these two events is one of the numbers below. Write the letter corresponding to the correct answer in the box. So we choose either A, B, C, D, E or F and put it into the box. So the correlation coefficient is B, or 0.77. So we choose B, 0.77. Note that in the graph, the data seems to slope in a positive direction. So that means the data is going uphill. It seems to be following a uphill slope or an uphill line. So it's not going downhill. It's going uphill, so positive. So we can straight away forget about any of the minuses, because the first three are positive, the last three are minus. So we're definitely going to have a positive correlation coefficient. Thus, the correlation coefficient must be positive, and so we can exclude D, E and F. If the data were close to being a straight line, then the correlation coefficient would be close to 1. So if all these dots formed very, very, very close to a straight line, a line of best fit, then we'd say the correlation coefficient is very close to 1, or it might be 0.99 or 0.98, and so on. If there is no linear pattern to the data, then the correlation coefficient would be close to 0. So if we could not see a line, we could barely see a line fitting in, we would say it might be 0.1, 0.2, 0.3, and so on. The data is not exactly in a straight line, but there is some linear shape to it. Thus, since A, 0.95 is too high, so A is too close to 1, so 1 would be a complete straight line, so A is too close to the number 1, so 0.95 is too close to 1, and C, 0.13 is far too low, so 0.13 is very, very close to 0. So that would be where we don't see any line at all, or barely see a line, but we can see there's a positive line that could fit in here. So we want a number somewhere in the middle. So it must be 0.77. 2. Frank was the slowest person in the run. How many people took longer to complete the cycle than Frank did? Looking at the graph, we consider the data point with the largest run time. So this is the run time, and we can see that this is the highest point. So this must be Frank. So this is somewhere between 35 and 40. So we would say that this is approximately 37.5 minutes. So Frank's run time is approximately 37.5 minutes. And the cycle is approximately 52.5 minutes. So about 52.5. We then count the number of data points which have a larger cycle time, which is 6 people. So the cycle times are along the bottom. So if this is 52.5, which matches up with Frank, there are 1, 2, 3, 4, 5, 6 people who had a greater cycle time than Frank. So 1, 2, 3, 4, 5, 6 people who had a longer or a greater cycle time than Frank. So the answer here is 6. Brian did not enter this race. Suppose that he had, and suppose that he had completed the cycle in 52 minutes and the run in 18 minutes. Explain why this performance would have been very unusual. Well, let's draw in where Brian would have been on our diagram. So 52 minutes for the cycle and 18 minutes for the run. So if this is 50 and this is 55, this is about 52. And if this is 15 and this is 20, then this is about 18. So here we see this is where we would plot Brian. So this is 52.18. And we see 52.18, this point here, this represents Brian. This lies very far from the rest of the data. So this is what we would call an outlier. So we can see it's not very close to the rest of the data because the data is going in a positive uphill slope. So it's getting quite close to a straight line. But this fella here, Brian, this would be an outlier. He's quite far away from everything else. He's an outlier. C. Maura knows already that the male athletes tend to be slightly faster than the female athletes. She also knows that athletes can get slower as they get older. She thinks that male athletes in their 40s might be about the same as female athletes in their 30s. She decides to draw a back-to-back stem and leaf diagram of the time of these two groups for the swim. There were 28 females in their 30s, 32 males in their 40s. Here is the diagram. So here's our stem and leaf. We have females on the left, 30 to 39 years. And we have males on the right, 40 to 49 years. And our key tells us that 14/9 means 14.9 minutes. So, for example, this 0 here is 23.0 minutes. This 4 here is 19.4 minutes. This 3 here is 15.3 minutes. This 2 here is 16.2 minutes, and so on. 1. Describe what differences, if any, there are between the two distributions above. So describe the differences between the female data and the male data. So the range of female group is 13.4 to 29.7. So 13.4 minutes to 29.7 minutes is the range for the females. So 13.4 to 29.7. The range for the male group is 14.9 to 23.0. So 14.9 minutes to 23.0 minutes. So the range for the male group is 14.9 minutes to 23.0 minutes. So the length of the range of the female group is double that of the male group. So the range of the females, 29.7 take away 13.4 is 16.3. And the range for the males, 23.0 take away 14.9 is 8.1. So 16.3 is pretty much double 8.1. So this could have been due to an outlier case, but there are several high values in the female group. So we see in the female group we have 29.7, that's very high, that's very far away from the majority. We have 26.5, that's quite high as well, and then 24.8, they're quite high, whereas we don't have any of those high values for the males. This implies that the times for the female group have a wider distribution than the times for the males. So these are the key phrases you want to be using when you're answering these questions. Outliers, wider distributions, range. As well as this, the male groups seem to have a symmetric distribution around the 17-minute section. So if we have a look at the males, we can see at about 17 minutes for the males, if we were to turn this sideways, we would see that this would be like a line of symmetry, or pretty much close to a line of symmetry. We have the same amount of values, are very close to what we have on the other side of the green line. So this is quite symmetrical. So this would be like a line of symmetry. So we would call this symmetric distribution. Whereas the female group seems to be skewed in favour of the quicker times, peaking at the 16-minute section. So if we have a look at the female section, we can see that 16, there's quite a lot of athletes who are in the 16-minute range. So we've got 16.2 up as far as 16.9. So the female section is skewed, so there seems to be more in the 16-minute range. Whereas for the males, it's quite symmetrical. So we seem to have quite an even spread above 17 and below 17. So again, these are the key phrases you want to be using. So symmetric distribution for the males and skewed for the females. So here we see we have just a summary of stem and leaf. So here's an example of symmetric data. So we can see that there would be a line of symmetry at around the 7 mark. So to the left or above the 7, we can see the values there. We have 4 values, then 3 values, then 2, then 1. And then below it we have 4, then 2, then 1. So it's quite symmetrical. If you were to turn your head sideways, you can nearly see a line of symmetry, like a mirror line. Here's an example of right skewed. So this is where the majority of the values are at the top. And then we have outliers at the bottom. And here's an example of left skewed, where the majority of values are at the bottom. And we have outliers at the top. 2. Maura drew the diagram because she thought that these two groups would be about the same. Do you think that the diagram would cause Maura to confirm her belief or change it? Give reasons for your answer. Maura should change her belief that the two groups have the same behaviour. The distribution of times is quite different for the two groups. So there is no reason to believe that they share any significant similarities.